And it's now my pleasure to introduce Professor Jans Funke from Durham University, who will speak about theta series and singular theta functions.
Thank you, Sol, for the kind introduction, and thank you to the organizers for inviting me to this workshop. It's currently exam season in the UK, and for all you have been involved in this in one way or the other at some point in your life, you know what kind of administrative nightmare this is, and I'm delighted to be able to escape, at least for a little bit at this point. I mean, Stephen mentioned his 3 kids and the pediatrician. I rather would like to deal with this than with exam administration. All right. So first, I would like to review a little bit positive definite theta series, and we start very, very classically and in a certain sense remain classical throughout the talk. So in the setup, V over Q is my quadratic space of dimension M, and you can assume M is even, you don't have to. In the previous talk, it was mentioned that if you don't assume this, then you have to go work with a metaplectic cover, which I would like to ignore for this talk. The quadratic form is 1/2 of the bilinear form, Q of X, and L is a lattice. So, and even means that it's contained in the dual lattice. And the evenness means that in fact it takes values, the quadratic form takes values in the integers, and the evenness of course comes from the fact that we divide here by 2. And with this data, we have the very classical result, which I here now attribute to Hecke-Schöneberg. Of course, it even goes back to Jacobi, the 19th century, that if V is positive definite, then the associated theta series formed by you sum over your lattice, and you look at e to the 2 pi I q of x tau, and you look at this as, or you form this into the generating series, where the Fourier coefficients are the representation numbers, how often the lattice L and the quadratic form Q take the value n, that this forms a modular form of rate m over 2 for some congruent subgroup of SL2Z, which I won't say anything about today. This is very much an Archimedean talk. The data at the other local places will go along for the ride. And slightly contrary to the conventions of the previous talks, my upper half plane variable is always tau, but Q is Q e to the 2 pi I tau. And of course, the analytic theory of quadratic form, as Hecke would put it, of course, has used this principle to great success for quite many applications about the study the arithmetic of these objects, particularly the representation numbers, and so and forth. We can play this slightly more general, namely, if you take P, a harmonic polynomial, homogeneous and harmonic of degree L, on your space V, and then you form the associated theta series in a similar way, then this function is also modular, in fact, a cusp form, and the weight has gone up by L. And we're still with the same congruent subgroup gamma prime. And for the proof idea, in its, if you want to, most concrete incarnation, we're using harmonic analysis. Namely, the function p of x times the Gaussian is an eigenfunction under the Fourier transform, and then you apply Poisson summation, and what exactly congruent subgroup is, this does depend on your choice of the level of the lattice L, which is not of our concern today. And we can turn this was also mentioned in the talks earlier this afternoon, into a bit more representation theoretic background. Namely, we consider omega the Weyl or oscillator representations. So if I now know how to spell oscillator, I can, the oscillator representation of the dual pair of the orthogonal group of V times SO2R. Here I cheat if M is odd. And I use the incarnation of the Weyl representation acting on the Schwartz space of V, or, oops, if you want to do this slightly more general, on the L2 functions on V. And then you have the basic principle that whenever you have a Schwartz function, which is an eigenfunction under SO2, sitting inside SO2R under the Weyl representation, say of weight K, then you can form your theta series, bringing in your variable tau into this, and then this becomes modular of weight K for some congruent subgroup gamma prime. And basically the proof works along the same way. And there is, in general, even in the way how I form this here is, in general, this theta series might not be holomorphic. For this, you need to wonder whether it's a lowest weight vector. Under omega, so under 4SR2. And of course, the Weyl representation exists at all primes. And so we have the Schwarz-Boer functions here, or at the finite adels. Then of course the choice of the Schwartz function of the finite spaces is really the choice of the lattice L. Or if you really want to do this representation theoretic in terms of automorphic representations, you go to the adults. But we don't need to worry about this today. Now, today it's rather all about what happens if V is indefinite. So I take my signature to be indefinite, P comma Q, and P plus Q is M, the dimension. So in particular, my quadratic form better be non-degenerate. And if you form the naive theta series from above here, you're running immediately into problems. This wouldn't converge, as Q of X takes negative values. And if you start with this expression here with the representation numbers, that wouldn't work either, because the representation numbers are infinite. So we have to worry about, so things are more complicated or more interesting in that setting. And however, I would like to give you one example, which I believe Don is in the audience, of course, in particular, been championed by Don Zagier as an example for an indefinite theta series, which you all know, and very well, namely the very classical Eisenstein series for SL2Z of weight, at least K, and of course even. And the Fourier expansion here is, of course, the Bernoulli number as the constant coefficient. And then we have here the quadratic form x times y, which is signature 1, 1. For my lattice, I take z squared. And if you want to, of course, this is a harmonic polynomial. Harmonic polynomial, and how do we get around the convergence problems? Well, I restrict to the positive cone. Namely, oops, this was not what I wanted to draw. Summation is restricted to the positive cone. And if you really, really wanted to, you could prove the modularity of the Eisenstein series in this way. Namely, you define the appropriate, well, I guess here the appropriate functions on your space, x to the k minus 1 times the indefinite Gaussian, together with the positive cone condition, and show by brute force that this gives you an eigenfunction under the Fourier transform. Maybe you don't want to do this, but in theory, one could. More conceptually, Siegel developed a much more general theory of theta series, at least of indefinite theta series. He was the first. So for this, he considered the orthogonal group of my quadratic space, and I'm looking at the connected component of the identity there. So that's SOPQ dot and the maximal compact subgroup K, SOP times SOQ. And suppose for everybody, this associated symmetric space G mod Q is very familiar. Familiar in particular for signatures, where one of the numbers is 1, 2, or 3. And what we will use is that this is also the Grassmannian of negative Q-planes. So all the subspaces of V which have dimension Q and on which the bilinear form is negative definite. G acts on this set transitively, and one given one is stabilized by a maximal compact subgroup. We can associate it to this a majorant, namely a minimal majorant. And I'm also proud to see is that I do believe Rainer Schulze-Piloth is in the audience, who ages ago actually taught me this and in lectures at the University of Cologne. So you can associate your majorant to this a positive definite quadratic form in the usual way. So if X is negative, is a negative definite subspace, you take minus of it. And if it's in the orthogonal complement, you leave the form alone. So, and this of course then defines you the quadratic form everywhere. We take gamma, a stabilizer in our still even lattice, and we look at the locally symmetric space, D mod gamma. We might want to assume gamma is neat, but we don't have to. In any case, we have here some very nice collection of objects. And of course, you all know that for 2,1, D is the upper half plane. X is either a modular or Shimura curve. P,1, we're getting hyperbolic P space. And in general, for P,2, D is Hermitian. And here I write down, really going back to Siegel, the so-called Gaussian, namely the function phi0 x, also depending on z, writing e to the minus 2 pi q sub z of x. And note this is of course not positive definite. Given x, it's a Schwartz function. It has weight p minus P minus Q under the Weyl representation. And again, the principle I outlined before applies. I mean, here I write this down in painful details, what actually the associated theta series is. The important here aspect is that now we have a function 2 variable in the tau variable. It's modular, but non-holomorphic of the weight P minus Q over 2. And in Z, it's a C infinity function on X. And the proof idea is really the same principle as what we had before. And we can play this for any Schwartz function or L2 function of weight L under the Weyl representation, and then we get, in generally, some non-holomorphic modular form on gamma prime. You do have to worry about a little bit about whether Poisson summation applies or not. And of course, this was also mentioned in Angesh's talk before, that then we have the theta correspondence here in its, if you want to, most concrete incarnation. You can use the theta function as an integral kernel in the orthogonal variable or in the symplectic, in the SO2 variables. And you get a correspondence, the theta correspondence of automorphic forms between SO2 and the orthogonal groups. And here in this way, not realized by House quotient correspondence, but rather by the integral correspondence using the theta series in an integral kernel. And of course, this goes back to, well, in this way I'll formulate this for quite a long time. There is, of course, Shintani and Neva in the mid-70s who realized the Shimura correspondence between integral weight and half integral weight modular forms in this way. Valls-Bourget looked at this in detail from the representation theoretic correspondence. And here I put some more names, and I apologize for everybody who's not on this, is in the audience, but not on this list. All right. So, but I rather don't want to look at the automorphic representation properties of the theta correspondence, but rather I'm more interested in the geometry of this situation. Namely, how can we study the geometry of X, or the cohomology either of the group gamma, or depending on what your flavor is, or of the symmetric space X, which of course amounts to the same thing. And one of the nice aspects here, geometric aspects, is that we have a very nice set of sub-manifolds, or at least cycles, in our locally symmetric space X. Namely, if you take your vector X of positive length, you get the cycle D sub X, which consists of all these negative Q planes, which are perpendicular to X. So Z needs to lie in X perp, which is really a subsymmetric space for the signature P minus 1, Q, which hence the dimension goes down by Q. And that sits, of course, naturally inside D. So this is really a way of embedding the smaller symmetric space into the larger symmetric space, depending on your vector X. If you look at gamma X, the stabilizer, this acts on this. If you look at the quotient, and this maps not necessarily injectively into, but it's still an immersion into your locally symmetric space, so you get your cycles. You can look at all the vectors of length n in your lattice. This is still infinite, but by Siegel, essentially the finiteness of class numbers, mod gamma, this becomes finite. And then you look at the collections of all these submanifolds now indexed by a positive integer. So n is here just a positive integer. And where does this lie? Just to space. So these are codimension Q cycles. In general, there might be with boundary as the same thing as X might have a boundary. But there are some of those, so this is defined over Z. And if we do this for signature 1, 2, well, then Zn are CM points, or if you want to Hegner points. So quadratic irrationalities in the upper half plane. For p, 2, so these have then codimension 1. Complex codimension 1, and some people call them Hegner cycles. I am not doing justice to the word Hegner here. Hegner cycles, or divisors, or special divisors, and so on. For 2, 1, we're still, of course, the symmetric space is the upper half plane, but in that case, we get geodesics. And here, of course, we get hypersurfaces for general hyperbolic space. So we get a very nice and very general collections of spaces and submanifolds. And the result of Kuttler-Milson is that, which is really the analog of what was happening in the positive definite case, is if you look at the generating series of these cycles in cohomology, then this becomes a holomorphic, an honestly Gauss modular form of the weight m/2, some subgroup. And where does this take value? Well, in the Qth cohomology. Meaning, whenever you apply a functional on the cohomology, you're getting an honestly Gauss scalar valued modular form. So for example, if you take a closed differential form here of the defining some class in Durham cohomology, you can integrate the differential form over the cycle, and you look at the generating series, and you get a modular form. And I should certainly mention here that the mother of all results of this type is the result by Hirzbo-Zagier for Hilbert modular surfaces of signature 2,2. And the proof idiom is that they explicitly form a theta series. And in fact, it's a co-cycle. What it really is, it's they construct a co-cycle, a cube co-cycle in the relatively algebra cohomology with values in the wave representation. And more explicitly formulated, this is a Schwartz function, which takes values in these are the closed Q forms. And it has weight under the wave representation of weight of m/2. You form your theta series, which you can because you have this weight, and you get something modular. And in fact, if you then look at this in cohomology, then this becomes exactly the generating series of these cycles, where of course here I happily omitted all the nasty details involved in this. And I'm not going to explain what the cycle would be for n equals to 0 either. But one aspect is actually important or amusing in this proof is, so I have this theta series, which in general I said was not holomorphic in tau, but here in cohomology, it becomes holomorphic in tau, it becomes a modular form. So is it already holomorphic in tau as a differential form on Z? And the answer is no. Only after you take cohomology. And this gives and since we're going to need this later, we'd like to give you actually the proof of this. You know, every talk needs a little bit of a proof. And the proof goes as follows. They construct another form, Schwartz form, of 1 degree less, and the weight is too lower, such that if you apply the exterior differential in Z, oops, that's the wrong variable. You get a Q form on the left. Then this is the same as if you apply the lowering operator in tau there. So you have this partial differential equation relating the orthogonal, the symplectic and the orthogonal variable in there is, and of course, Sol, the other Monday actually looked in your thesis, and I did see already some of these differential operator places already occurring there as well. For signature, was it 3,1 or 1,3? Either one. And what that really here happening is there is a certain double complex going, namely D and the del bar complex going. So we're really doing some calculation here in the spectral sequence of this. So that's really what was really behind this phenomenon here. And then the consequences is that if you pair your theta series against the closed differential form, this becomes holomorphic and then becomes the generating series of the cycle. And I cannot resist giving you the proof. So we do need that this is better be 0 if you apply del bar tau. Well, we can pull this in because it's in the other variable. It's in there. But by the equation here, I can move this. Well, first of all, I can move it in here. And then, of course, I can apply this here. So therefore, what I have here is that then this becomes psi of q minus 1d. Eta is, of course, closed. So I can apply Stokes theorem. I'm over here. And now I declare victory because Eta was compactly supported. So the boundary value is 0, even if you're in the non-compact case. So it's a beautiful dance of differential, of the of the differential operators. Or another way of saying this is if you look at phi q in the relative Lie algebra complex as viewing this as an SL2R representation, phi q is a lowest weight vector. I can't resist, because the non-trivial local systems were mentioned earlier this afternoon, that one can generalize this, and I did this with John Milson, to non-trivial coefficient system in quite great generality. So much for the background. I'd rather want to talk about the construction of Green's functions in singular theta lift. And I will restrict here, at least for the moment, to the orthogonal group OP, 2, or if you like 2, P better, that's of course fine as well. So V was my quadratic space of that signature. Dimension is P+2, which is M. I have my Hermitian symmetric space D, and the complex dimension is P. I have my lattice, I have the stabilizer, and I have my my space X, which here is by result of Bailey-Borel an algebraic, a quasi-projective algebraic variety. I have the cycles, which have complex codimension 1 on the symmetric space, on the locally symmetric space, or if I use them with the integers, parameterize them by the integers, Z of n. So just as a review. And I mentioned here before the equation here. In fact, here, in that case, we can go slightly more general about this and namely, if we take phi 2, which was the Kuttner-Milson-Schwarz function, which is a 1-1 form, Schwarz function, and phi 0, the Gaussian, one has weight m/2, the other has m/2 minus 2, that then we have the equation which we had before, but now one step further. It's del z in phi 0. This is now in a 2 form in z, that this is the same as del bar tau, so del bar in the tau variable for phi 2. It's the same equation. Since I have here now the additional information of a Hermitian space, I have more differential operators. It's not only, if you want to del exact, it's del bar exact. And it's actually quite nice calculation in the Weyl representation to check this by hand. And I will refer to this later on as the Milson equation, as John has in particular the champion of this way of looking at these things. So I have these objects, the Schwarz function with values in the differential forms and the Gaussian, and now I can play with this. And the first thing is you can form what I call the Green's function of Kuttler type. And in that case, actually, Steve constructed it on the nose. And namely, what you do is what that really is, you undo the tau bar here. You're looking at an antiderivative in tau. And for this, what you really do is what you can do is you look at the Gaussian and integrated it here. So you look at this integral. And this actually has singularities. In fact, logarithmic singularities. Along the cycle dx in D. but otherwise it's a beautiful function. And at least formally, I can also view this as a function in tau. And I have undone the del bar in tau variable, at least formally, and this is justified by the theorem which independently Steve Kudler and Jan Bonnier and myself proved is, if you look del bar of xi, you get indeed the differential form in the Kudler-Milson theory. And this is right on the nose as differential forms on D outside the cycle. And if you apply tau bar on it, you're getting back phi 0. And that's what I meant with you're really undoing this equation here. You're integrating with respect tau, both sides here. And this is why it nicely works, except you pick up this singularity. And when you have these objects, you of course do want to wonder how does this work as a current? Is there a residue? And the answer is yes, and that's the current equation going back to Kudler. So you take your test form, so P minus one form with compact support, and you take del bar of it, you get a top degree form, which you can integrate against the function. And what you get is, you get the integral of omega over the special cycle plus the integral of the two form, the non-singular two form against omega. And that's exactly the Green's equation, and that's really what it makes it a Green's function. It's not the standard one, but it beautifully works. And there exists a global version. I mean, I formulated this here for my convenience, only for on the symmetric space as well. You can do this by basically summing up both sides over all vectors of length n to lift this to the symmetric, to the quotient z of n. Question is, why do you want to do this? And Kudler developed this vast program, the Kudler program, we call it now, which is really the idea is of upgrading the modularity of the generating series of the special cycles from cohomology to arithmetic geometry to the arithmetic child groups, say, as developed by Gilly and Sully. But it's also quite handy to have this Green's function as a computational tool available in the theory of indefinite theta series. And let me just give an incomplete list of names who have thought about this in one way or the other recently or not so recently. I think it goes, of course, back to Zaghi, Sanders Vegas. Then a few years ago, Abramovich, Banjari, Manshot, and Piolin worked quite extensively exactly in the signature P,2 on this. Nazaroglu looked at the general signature. Steve then realized that one can do this in this theory. Martin Raum is also in the audience worried about this as well. And Steve and I wrote also a couple of papers on this as well. So as a computational tool, it's very, very handy as well. Now, so that's one way of constructing Green's functions to these objects. There's another way of doing this and this actually comes from theoretical physics originally. So, and to make my life simpler, let me call kappa p plus 2 over 2. K is the dual weight 2 minus kappa. And I let M here to be the space of weakly holomorphic modular forms, which are your regular holomorphic forms, except that you do allow for poles at infinity. And note, you better have to allow something here, because typically your weight might be negative. And then Bonnier and I looked at an extension of those, namely what we call, now it's called, are the weakly harmonic forms, which, as the name suggested, are harmonic. They have exponential growth at the cusps. And when you apply essentially del bar again, you end up in the dual weight 2 minus k. This is not positive typically, and you get a cusp form. So these are this kind of differential operators, which, of course, Stephen, not quite in this way, wondered about today, earlier this afternoon. And the result, in fact, is that the Xi operator here is surjective. You can get a primitive for all cusp forms in this way. And the kernel are, of course, the weakly holomorphic ones. What is more relevant for us now is that you can use this to construct singular theta lifts. So you take F, your weakly harmonic, your weak harmonic form, and you integrate this against the regular Gaussian theta function. And the point is that here the weight of the theta function is minus k. This has weight k. Together it has weight 0. You can integrate it against the Gaussian, and you're getting something which is invariant. And at the end, you're getting something on the orthogonal side. Of course, the problem is that this needs to be regularized. And in the process, you get singularities along cycles, or here the divisors, ZF, depending on your input function, but this is a finite linear combination of these ZNs. So, and this was originally proposed and carried out in great success by Harvey and Moore, and then picked up on the mathematics sides by Borchertz. And they looked at this when F is actually holomorphic or weakly holomorphic. And this then led to automorphic, or Borchertz products, as at least the mathematics people call them. And very, very roughly, you take phi and you can exponentiate phi to get an automorphic product, an infinite product. But then shortly afterwards, Bonnier and his collaborator, that was Ulf Kuhn and myself, in various incarnations, we looked at this when F is indeed not holomorphic, but harmonic. And the next thing is that, again, you satisfy the same set of the same current equation from before. Namely, if you look del bar of your current, so you integrate phi against del bar of your test form, you get the integral of your test form again over the cycle plus the standard error term. So it's again a Green's function. Yes, a Green's function. And what is this Green function? Well, that's what Brunier and I determined, and what we refer to as duality, namely, well, up to some multiple of the Kähler form. Note, this is a function. You get a 1-1 form, so you can get your Kähler form, and then what you get is, well, you do want the theta function associated to phi2, tau and z, which is the 1-1 form. But you do need to get rid of the tau variable. And you're looking at the Peterson inner product of weight m/2, which is kappa, in weight kappa. This is the additive Borchertz lift. You take del bar, it becomes smooth. The logarithmic singularities go away. Get a multiple of the Kähler form times, take the Kuttler-Milson theta series, 1-1 form, modular in tau. You take f, turn it into a cusp form, take the Peterson inner product, and there you are. So, and that's how we were able to relate the singular theta lifts to the ones in, to the more classical ones, at least with the geometric interpretation. All right. And now you have two Green's function, namely the one of Kuttler type, and then the one which arises from a singular theta lift. And you might want to compare them, which I won't go into this, but this was done by Ehlen and Sankaran. Essentially, if you look at the difference of them, form a certain generating series, you're getting something modular. And Oda Suzuki used similar constructions, well, constructed similar or related Green's function using entirely Lie theoretic methods. There is no theta pair there. All right, which raises the question, can we do this for other groups or other dual pairs? Say, for example, here we had OP2, if you want to, with SP, and well, usually I'm an SPN person, but let's call them SP2N here. This is, or you might as well think about unitary groups. Dual pair UNN, where then you would want to try to get Hermitian modular forms. And the theory I developed so far is only restricted to divisors. Can you do this for higher dimensional co-cycles? And the answer is yes, and that's what I would like to present today. And for this, we're going back. We're getting the color out. Namely, we look at this for the unitary group UPQ. So then V is now a Hermitian space. So you have your Hermitian form is, and the signature is actually quite general, P plus Q. So, and here, of course, you are not over K, over Q, but over, say, an imaginary quadratic field. And so the dimension I still call M, which is P plus Q. We still have the big unitary group. I can look at the quotient, which is now has dimension, complex dimension P times Q. And I can again realize this as the negative Q Grossmannian in V tensor R. I can still have my lattice, my stabilizer. I get my quasi-projective algebraic horizon. I can get now in the same way as before my cycles. So these are the z's in D, which are perpendicular to x as before. I get them in the quotient. I can sum them up, again parameterized by positive integers, but now they're having codimension q. It's codimension q, so they have higher codimension. I'm away from the divisor situation. And well, what do I have? I still have the Kuttler-Nielsen forms in these ones, which are now, let's call them phi QQs, because they in fact QQ forms on my symmetric space, which have no weight m. In the unitary group, you always double the weight as m, and we do have a form xi, which is a q minus 1 form now, which has weight 2 less. And this theorem is now due to Erich Hofmann and myself. So we still have these forms. We replace the Gaussian by the primitive for the equation there. And here I'm getting Q. So it's the same equation you can solve. Now in the different dual pair, you look at the geometric theta form. Before it was a 1-1 form on the orthogonal symmetric space. Now it's a QQ form on the unitary, in the unitary universe. And we still have this. So what underlying this is we really have the dual pair UPQ with U11. But of course, U11 is, and please forgive me that I'm forgetting this, essentially SL2. So on the other side, we still have SL2 to work with, and this becomes now quite crucial for what will happen in the following. Well, how do I now form a Green's function of Kuttler type now? Okay, type. So that's again Erich with myself, where we replace the Gaussian, which was what we had here before for the big equation here, with the one which solves the equation here. We had the phi QQ God given. You can look at this. Can I solve this equation? Yes, I can. With xi, and I take exactly this to the series. Again, we're getting, well, maybe since we're no longer talking devise, it's not quite a logarithmic singularities along the cycles. And I again have the same package as before. If I, well, maybe let's label this using the x's. If I look at this object now, which is a q minus 1 form in the unitary symmetric space, I take d dz, I get a q comma q form. And what is it? Well, it is exactly what you hope it is. Phi q, phi q. And if I apply del bar to it, I get xi back. So the constructions so far were completely functorial. All the decisive point was that you're able to solve this equation. You have this, you look at this, and then you need to solve this partial differential equation, which you can completely working in the real representation. So, and then you have the current equation. Again, Eric self. So this all beautifully works as a charm. You get the test form, which now, however, is of higher codimension. So there's a Q here and a Q here. And what you're getting is, well, the same equation as before, still holds. You get the integral over the cycle plus the one coming from the KM forms, the error term, if you want. And there are various proofs, so this is, I prefer a very lead theoretic proof for this, and there are a global version again for this. So this works like a charm. And again, you can use this in a Kudla program, but it has not sufficiently explored this. I don't think anybody has so far looked at this for these constructions in terms of constructing indefinite theta series for the unitary group. But then we can play the same game to define a singular theta lift, which now won't take values in the functions on the orthogonal symmetric space, but in the forms on the unitary symmetric space. So kappa now is m. Before that it was m over 2, so it's n here is, and the dual weight is, well, is 2 minus m. I still have the weakly holomorphic and the harmonic forms. I still have this. And I use the theta series associated to the auxiliary form xi, the one which solved the partial differential equation, to define your singular theta lifts. So if you want to, this is an axiomatic view of viewing singular theta lifts, is the proper kernel function for singular theta lifts is the one which solves up there the differential equation. You still have to regularize, you get singularities along the cycle ZF. Okay, here I have to say, well, since I'm no longer talking devices, we will not have automorphic products in this way unless, of course, Q is equal to 1. And that was in fact done by Eric Hoffman in his PhD thesis. But it hasn't been quite explored sufficiently what you can do on this side geometrically if you do put in something weakly holomorphic in the lift. So that's, again, some open question, not been done. And then we have the result. So again, Eric and myself is, so if I look at the P-1, Q form, so high dimensional one is, then I get the same current equation as before. So I have this, I have the entire package again, and indeed, I get the duality result. I need to change some variable here. This one here, phi QQ. And here, you get an appropriate chant form over there. So you're getting the same duality package again. This should already give rise to quite nice applications for, again, in arithmetic geometry and part of the Kutler program. But let me move away from this and rather wonder, now what? Further remarks?
John's, we're at 45 after, so just try to keep a few more minutes if you can.
I'm done in 1 minute. Sorry. I thought
it's fine. It's fine. Please finish. Take a few minutes just to warn you about the time.
I was doing great.
It's all good.
I still had 15 minutes. Oh God, sorry. Yes, one, and that is just 1 minute.
It's all good. Don't worry.
So, what about these higher dual pairs? Well, we do have a KM theory, and we can solve the Milson equation, which is the crucial differential equation, which I mentioned before, and we can do this in general. So that is, on the representation theoretic side, no problem. And in fact, Garcia and Sankaran, using a different approach, rather using Quillen's theory, use this of the construction of green forms for higher codimension of the Kutler type, for higher codimension n in the orthogonal group or nq in the unitary case. It's still not quite open whether that's the same, whether it was what we have been doing, but it should be, and they use this quite nicely. The problem with singular theta lifts is that the naive input space of weak harmonic forms is empty. There's basically the Köcher principle in your way in the symplectic case for higher dimension. Brunier found a way of getting around this for real quadratic fields in the Hilbert modular case using so-called Whittaker forms. And that's roughly your usual Whittaker function. However, you look at the bad solution, the one which has exponential growth as you go out, and not the one which is nice and gives rise to Cus forms, to Poincare series, to Cus forms. And together with Jan and Steve, we upgraded this to the symplectic side with quite some analytic pain. Unfortunately, that's still not enough to get the singular theta lifts going. Just writing down an integral won't do, or it's so unmanageable at this point. And so here, this is an AIM working group. So that's Jan Bonnier, myself, Steve Kutler, Siddharth Sankaran, and Tongha Yang. So we are trying to get this going with the input we have, with the Whittaker forms and all the other ideas. So, and that's work in progress. So sorry for going a bit over time, and thank you.
So let's thank you very much, Jans, and let's everybody please thank Jans. I'm going to turn off the recording now.